from the Wrocław University of Science and Technology, Politechnika Wrocławska, and the title is Universality of K-shifts. Please.
Thank you very much. It is always my pleasure to visit Impan, where I spent 2 years on sabbatical.
End of 70s?
No. Oh, you are talking about my internship or how?
Yeah, I understand.
No, but later, 7 years ago. Anyway, so let me pass to the topic, universality of K-shifts. This is based on a joint work with Benjy Weiss, Mateusz, Więcek, who was here last week, I guess, and Guohua Zhang from Zhang. So the story goes like this. Oh, it says motivation, but it seems that the titles of the pages, unless you type the menu.
Ah, not this one.
Oh, thank you. Okay, sometimes the titles are essential. This one is essential. So, yes. Okay. So the topic was suggested by Benjy, who wrote to me, and later he sent a sketch of an argument for residually finite groups, and this was nearly the time when me and Mateusz visited Guohua in Shanghai. So I proposed to develop this subject that Benjy suggested. So this is why we have so many co-authors. Okay, so quite recently, for some time we were happy that everything works, and what Benjy suggested is a good conjecture. But just 2 days ago, it turned out that the conjecture, as it was stated, is wrong. There is a counterexample. It's not awfully wrong. It just requires a small additional assumption. And then also quite recently we discovered that basically all the time when we proceed with a proof, we are using a weaker property. So the conjecture with this additional assumption holds for a larger class of systems, and that's why K-shifts turn out to be an example rather than the main setup for this story. Okay, so what are K-shifts? We work with infinite countable amenable groups and actions of these groups on shift systems. And in this case, the shift will have two symbols, 0 and 1. We choose a subset of the group finite, and we want it to contain the unity and at least one more, so it's not trivial subset. And we call a set A, K separated, if the shifted copies of K, Ka are all disjoint for A in A. So here is a picture. The black dots represent the elements of A. The funny shape is the set K, and as you shift it, they are all disjoint. Of course, thinking on the plane is very tricky. It's good for getting the first intuitions, but the groups we are dealing with are sometimes much different from the plane. So the intuitions from the plane sometimes fail. One has to be aware of that. Okay, and a K-separated set is maximal if it's not containing any larger K-separated set, and which is easy to check. This is equivalent to the following, that the copies, the shifted copies of not just K but K minus 1K, they cover the whole group. So K minus 1 Ka equals G. Here is the illustration. This is our shape K, and the larger shape is my awkward imaginary representation of K minus 1 K. And the black dots are a maximal K separated set. Okay, so Benjy proposed the following notion. The K-shift is just a collection of all maximal K-separated sets, but we want a subshift, so we represent the set by its indicator function. And in this manner, we get a subshift on 0 and 1. It's an exercise to see that this set is closed and shifting down. And Benjy proposed the following, that the K-shift omega K is universal for entropy less than the topological entropy of the K-shift. So first of all, we need to understand that the topological entropy of the K-shift is positive, otherwise there is no entropy less than that. So I will explain that in a moment. What means to be universal for entropy less than some number? It means that every free ergodic G action on a standard probability space, also mu, with entropy strictly less than that number, which is in this case the entropy of the K-shift, there exists an invariant measure on mu which is isomorphic to mu. So you can find a model of anything with appropriately small entropy inside the K-shift. What means that the system is free? There are two notions of freeness. Well, there are more, but one is topological. The topological system is free if no point is invariant under no element of the group except for union. But for the measure theoretical setup, we always require something to be true almost surely. So G system is free, measure preserving, if for any element different than E, this set has measure 0, the set that is fixed by G. Okay, so before I go on, I will explain the property which turns out to be the crucial one in this story. That is the specification. And the first place where you need specification is to see that omega K has positive entropy. Of course, you can prove it in a different manner, but with specification it will be quite simple to do. So what is the specification? We take a shift system on a finite alphabet, of course at least two elements, otherwise it's 1 point. We say that it has a specification property with margin M. M is non-empty finite set, preferably containing unity, but it doesn't matter. If for any two subsets such that their M enlargement, I would say, are disjoint, any pattern that appears on F, any block, however, block is usually understood as something finite. The sets F1, F2 need not be finite. So anything that you can see on F and on F2 within X can be joined. So on the union of F1 and F2, you have a pattern, and this pattern should be also admissible in X. That means that there exists an element X in X such that restricted to F1 matches the pattern on F1 and so on. So here is the, too small. I will tell you what it says. The blue set is F1, the red set is F2. Actually, the blue is the symbolic lock on F1. So F1 is just the domain of this thing, F2 is the domain of the red thing. Blue is some symbolic lock, and the same for red. And this pink stuff is the enlargement MF1, here is MF2, and this says can be filled. So you can find some symbolic content on both the green and the pink, so that the whole thing is admissible in X. Okay, so this is And we have the following relatively easy exercise that any shift with specification, with any margin, has positive entropy. And you will see that the easiest lower bound is log 2 divided by cardinality of m squared. I will give details of that in the second part. So let's go back to k-shifts. We have the following exercise. That's not that easy anymore. Namely, you will see why, because a strange set appears. The k-shift has specification with margin k minus 1k. I was really surprised. At the first glance, I thought it's just k. Then I thought, okay, we are dealing with k minus 1k a lot. So I was sure that k minus 1k is enough. And I asked Mateusz to work out the details, and he came to me back with this.
What k was just a finite set?
K is just a finite set which defines the k shift.
So do you have examples when k inverse k is not efficient?
Well, given enough time, one could produce such an example, I'm sure. But I didn't. I was too lazy. Anyway, I will, in the second part, maybe I am not going to prove this because it's very technical and Mateusz has the proof. But I will show you why k is insufficient, or even k minus 1. If I have enough time, I will tell you why. Because this looks quite weird. Okay. So I start with a counterexample which turned our work upside down. Benjy's conjecture, as it was stated, without any additional assumption, actually is wrong. And the simplest counterexample is commutative. It's the group is Z times Z6, the cyclic group of 6 elements, and we take k to be 3 points. This is the unity of the group. This is 1, and 5 is the same as minus 1. So this set is symmetric, which also sort of takes away any hopes that a symmetric set would have. Okay, so here is the picture. I don't know why I made these pictures so small, I'm sorry. But on my screen, I know why, because recently I received from my institute very large 2 screens. And if I show it on my screen, it really looks very readable. Then turns out that it's not that. So here is the Z6, each of these hexagons, and then they are distributed along Z. And finally, here is the set K, which is symmetric. And you can see that within Z6, the only point which is separated from 0, 0 is 0, 3. Because if you imagine the copy of K centered at 0, 3, it will be exactly the 3 remaining points. So that means that any K-separated set A, for any n, if you intersect with a coset, so one of these guys, it is either empty, of course, or contains just 1 point, or if it contains 2 points, it must be Ni and Ni plus 3. And if you want a maximal separated set, then empty and just 1 point fall out. It must be the third option. So each maximal set looks like the red dots here. Can you see the red dots? So it's always something on the coset and then the opposite point. But of course there is still a lot of entropy possible here because you have 3 symbols on each element of Z. But if you rotate this set by 0, 3, you get the same set. So the element 0, 3 acts on the subshift by identity. And then there is, of course, no hope to get any free ergodic measure or non-ergodic measure. It doesn't matter. If you talk about free measures, if the measure is free, then the components also have to be free. Okay, so So here is our main theorem, which now is true. A G subshift with specification is universal for entropy less than the entropy of the subshift. Oh, it's a typo here. It still comes from the old version. There should be h top of x. If and only if it carries at least one free measure. So the condition is very strange because you first need to be able to find one free measure supported by this subshift, and then you know that it's already universal. It contains plenty of free measures, but you need one to begin with. However, this condition can be simplified a lot, because if a subshift has specification, then it carries at least one free measure, if and only if no G acts as identity.
So what is free measure?
Let's go back a little bit. No, still a little bit. Here is free if for any G, it doesn't fix anything essentially. Okay. Oh, I'm going back instead of going forward. There is no such thing as a button that jumps 5 pages forward.
But you have that below a lot of.
This requires you to be more.
Yeah, drop with this and drop it.
Yeah, first world problem.
Right. So again, if a subshift has specification, then it is enough to show that for each G you have just one point which is not fixed by G. And then specification takes care of making this one X into something a positive measure. So you have a following version of theorem 3, which is much more user-friendly, because it says that the subshift is universal for entropy, still typo, entropy of X, if and only if no G acts on X as identity.
Isn't this called faithful?
Faithful?
It's a property.
I know faithful as a different notion, but
So maybe no, I don't know, I'm asking.
no, I don't know. Ask Benjy. He knows the terminology much better.
הרב מקשיב של תומאס באימפן.
Yes?
אני אדבר איתך יותר מאוחר, אולי בשתיים. להתראות.
Later.
Okay. So back to K-shifts, we want to study this condition a little bit more. So if a group is commutative, we have an equivalent condition which is easily checkable. And it says the following: G is abelian and the set K is finite. Now back to K-shifts. When does a K-shift has this property that allows it to be universal? So K is as required for the definition of the K-shift. And an element acts, so I'm formulating the negation of the condition. An element acts on omega k as identity if and only if the following condition holds. So I will draw now on the blackboard. It's quite simple. You have your set k, actually k minus 1k. And you multiply it by G. Because K contains unity, you will definitely get G. And the only thing you want to lose is E. So you want to replace E by G, and otherwise you want it to be kept. Which is exactly the case that I drew on this figure. Right? This was G, this was K minus 1. K was this. This is K times K minus 1. K is symmetric, so this is K squared. And if you multiply this by this point, you will get exactly this set, and you're losing E. Clearly, if G belongs to K, or to K minus 1, this is not going to happen. Because then kk minus 1G contains the unit. And by, so this is not happening. G must be outside. You can check that G must belong to the fourth power of K if K is symmetric. Why? Because K contains something other than unit. And if you use this point here in these formulas, you will find a formula for G that uses 4 elements. So we can formulate a theorem for K-shifts, namely, if G is abelian, then a K-shift is universal if and only if there is no G such that this happens, which is the same as here. So we have a very nice theorem for K-shifts. It's a modification of what Benjy suggested via this one condition. What happens for non-abelian groups? For non-abelian groups, we also have a necessary condition, which is very similar to the previous one, but by lack of commutativity, we have to assume a little more. So again, this is the negation. This is the bad situation. If there exists an element different from unity such that for all A in G, K minus 1K AG equals K minus 1K A minus A plus AG. So again, you replace one point. The tricky part is that A is between K and G, so you cannot cancel it. If the group is abelian, you can move A here and here, and multiply everything by A to minus 1, you get back to that condition that was given for abelian groups. But here you need this. Then G acts by identity, so it's a bad situation. We also have some situations which suffice for this theorem to hold. I will name 2 of them. Namely, if K is finite subgroup, K itself, the set which we choose to define the K shift. If this is a subgroup, then this is not going to happen. Or if G is torsion free, then again, no G acts by identity. So this is it. This is the end of my slides. From now on, I plan. Yes.
Do you have examples to theorem 6? I mean, examples when G acts on a K by identity, but this condition is not satisfied? So showing that this is not necessary condition.
No, this is the negation. If this condition is not satisfied for any G, then everything is fine. So you want a counterexample that this condition, which I call necessary, is insufficient.
Yeah.
No, I don't have a direct example, but it seems very likely, because anytime you violate this, you can show that G moves some point on the K shift. So, but we were unable to prove that this is an equivalent condition. And it's still, I doubt that. Okay, so now I plan to give you sketches of the theorems. And this I will do by hand. So I don't know if your camera is selected. Yeah? Is it okay to be here? Ah, that one. Okay, so
You can see it on the screen. You can see the camera on the screen.
yes, that's right. Okay. So the sketches of the proofs are really very simple. So there is no citation of any deep results or anything like that. Everything is finger counting. Okay. So how do you prove that a G shift with specification has positive entropy? Again, here you go back to the notion of a K shift. So you take a maximal K separated maximal M separated set. There exists such a thing. So here is your maximal M separated set. This is M around those points. You know that they are all disjoint. The symbol 1 is clearly admitted. The symbol 0 is also admitted in the system with specification, unless it's completely trivial system, that everything is ones, for example. We eliminate those things. We want the alphabet to be at least 2 symbols, and we want both of them to be used. Otherwise, it's just cheating that that there are 2 symbols because only one, use only one. So both symbols are admitted. Now all these sets are pairwise M separated. So you can put 0, 1, 1, 0 as you wish. And all these patterns are admitted. So the entropy is log of 2 divided by the area, because the density of the M separated set is at least 1 over M squared. No, 1 over M actually. So maybe it should be 1 over M. So this is the first exercise which I told you is
1 over M squared.
squared.
Yeah, because M squared covers.
Yes. But what is the density of this set?
You only know that 1 over M squared
I know.
that covers. This may not, there may be bigger holes. You don't have an exact packing.
Right, but no, wait a second. If I know that the copies of M are disjoint.
Yeah, but there's more empty space.
Right.
Imagine the shape being diamonds.
Squares.
Not squares, diamonds.
Diamonds.
Curved diamonds. Curved diamonds. And then you can't.
Beyond my imagination.
What?
That is beyond my imagination. Curved diamonds.
4 hyperbolas.
You want this? Like...
Yeah. But very long pieces.
Okay.
Long pieces. And now how do you make them disjoint?
Okay, I know that they are very far apart.
Yeah, so the density is not 1 over M. The density 1 over M, M times has to cover.
Right. Yes, that's right. Okay. So I wrote it. You see, I knew.
Yeah. It's okay.
I just got confused while I.
Yeah. I'm sorry. I shouldn't interrupt you.
No. That's fine. All right. So we are done with this, and then theorem 2. Any K shift has the specification with margin k minus 1k. So I'm not going to do this because it's really technical. But I will show you why just margin k is insufficient. That will give you enough flavor of what kind of difficulties we are dealing with. So imagine that I have a set on which I have a pattern which comes from a maximal k separated set. Okay? And imagine that somewhere here in the original, because this pattern comes from some X, from some element of the K-separated, of the K-shift. So there is a larger K-separated, maximal K-separated set. And imagine that I have a dot somewhere here. And I could have had a dot here if I don't have this one. So this pattern is okay, it appears in some maximal case separated set. And then I take another set, but I remember I don't have a dot here, but it could be there if this wasn't there. So now I take another pattern and I want to fill in the whole thing. So it may turn out that I will put here a dot, and that I will be forced to put a dot here. So that means that because of what happens here, or maybe closer to here, I have some dots here. These dots make this dot impossible, because there is one here which is too close. So this one is impossible, and then by maximality, I must put a dot here, even though they are separated by K. There is still some influence. It's not that some of the dots here are forbidden in my joint pattern, but it may happen that some of the empty dots have to be filled in. So this is the kind of influence that goes from farther out than just K, or KK minus. Okay, so if you find out this phenomenon, you have to work out the proof, which is much more complicated than you imagined originally. Okay. So these are details. Okay, now we have proposition 1 that a subshift with specification carries at least one free measure if and only if no G acts by identity. So how do you prove that? Well, okay, it will be just a sketch, but I hope you will enjoy. So you take a dot, so element of the, you take a symbol, maybe some symbol A at some place, and you know that there is an X such that G does not act by identity. That means that there is a point in the system such that if you go by G, you will see a different symbol, B. This configuration is possible. So now you can take these 2 points as your F1, and then if you go far enough, you are separated. So, sorry. What do I want to say? Yes. So, what is our goal? Our goal is to create a point which will be generic for some measure, where this situation will appear with positive density for every G. Okay, because if I have this situation with positive density, and the point is generic for some measure, then I know for sure that for this measure, G does not fix a set of positive measure, or the set which it fixes is of measure 0. So what I need is I need to distribute these pairs with positive density, and then I change my G to another element, maybe like this, and I need maybe C and D, and again I need to distribute these guys 6 arrows with positive density, not colliding with the previous one. And I have to do it for all countably many elements. So I will roughly tell you how to do that. It's not so difficult. However, if you want to write out the proof, you will spend a day. But to explain with waving hands, it will take 2 minutes. So you know that this pattern is admissible. You go far enough so that these two are M separated. So you know that this pattern here and this pattern here are acceptable jointly. And then you do it again and again and again. And because you can do it so that this A is separated, or this pattern AB is M separated, you can show that if you take the maximal set allowed for this pattern, you will have something with positive Banach density, so it will have positive density. Fine. Now you go with another G. You do the same, and you have to do it maybe not a maximal separated set, maybe a little smaller, so that the density of what you've done here is much less than the density of what you've done for the first G. First of all, you have to enumerate your group, G1, G2, and so on. And this was my G1, and this is my G2. So you've done it for G1. Now you do it for G2, but your density that you are using is much less than the density that you created for G1. Yes?
So when you say do it for G2, you mean you build...
You take this pattern, which exists in some X, you distribute it with, so that these patterns are M separated together. But M is not good because you will get too large density. So you take maybe M cubed or M to the 7th. You take a larger separation. You still know that this will happen with positive density because your M7th is finite. But you know that the density that you've created for G2 is much smaller than the density of G1. So now you go back to your G1 and you remove all patterns made for G1 which collide with the patterns for G2. But because the density for G2 was much smaller, you know that you keep enough of G1 to still have positive density. Then you go for G3, and then you modify G1 and G2. Each time you remove a little bit, but you control how much you remove. So in the end, you will still have something with positive density. And this is a big lie, because by removing single points, even single points, you can destroy a set of positive density. So this construction requires a small modification, but I'm not going to describe it. It's a little technical. You have to remove it so that you avoid a situation that you destroy the whole set. You must do it so that you have some kind of countable countable additivity of density, which we know doesn't hold. But if you do it wisely, you will have countable additivity of density. So if you remove from G1 the sets created for G2, G3, and so on, and the series of densities is summable to something less than the density of G1, and you do it wisely, you will keep the difference for G1, and so on. So this is the kind of constructions that you need to push forward.
So how do I obtain the measure from this?
So you take any measure quasi-generated by this point. And because you have Banach densities, lower Banach densities, bounded from below, you know that any measure quasi-generated along some Fellner sequence, which, by the way, interferes with a step of the construction which I skipped. So you choose some Fellner sequence, and this modification that I told you depends on this Fellner sequence. In any case, in the end, you take anything that is quasi-generated by this point. Every point generates, quasi-generates at least one invariant measure. And for this measure, you know that this pattern appears with positive density, this pattern appears with positive density, and so on. For all G, you have positive density of, which translates to positive measure of the cylinder, which has these two. So on positive measure, you.
I didn't understand your remark because it seems that there is an older problem here. You say that you know a priori which Feynman sequence will be used later in a priori.
You can fix any Feynman sequence. The only thing is that in the end, you need to what?
To get the subsequence maybe.
Yeah, convergent to some measure. Okay, so then practically almost every point with respect to that measure will have this pattern appearing with density. It's enough that it will have it once, because we want this point not to be fixed by G. So it is enough that it has only this. Okay, so you use ergodicity also for, you choose an ergodic measure and so on. It's standard. But the main part is here, in choosing those patterns disjointly and so on. Okay. Let's go on. We have theorem 4 for abelian. And this one is also quite obvious. Actually, the example that I showed you already had the whole idea in it. So if you have an element such that multiplication of k minus 1k by G only exchanges one point, E falls out, G goes in, then G acts by identity on the K shift. So how do you prove this? Well, actually, the proof is the same as for the example. If you look at some dot, suppose you have a maximal K separated set. You take a dot, which is little a, and you know that you look at k minus 1k, and you multiply this by G, and the only thing that changes is that, because the group is commutative, this condition is equivalent to this one, k minus 1k, G, and you can multiply by A any way you want, equals k minus 1, k, A minus A, and union AG. So this is equivalent, and I want to write A in here and here. So that means that this point is AG, and if I remove A and include AG, this is going to be, now this is going to be k minus 1 times G. So the point AG, if you draw k minus 1 around it, it does not contain A. So that means that the pattern A and AG is admissible. It is admissible because they are separated. And AG does not belong to k minus 1, so these two are k separate. On the other hand, inside k minus 1 G, AG, that's right. Inside this set, you already have put one point, and there is a rule in maximal case separated sets that it actually in k-separated sets, that if you have something, if the center of your shifted kk minus 1 is occupied, then nothing else in this set can be put. So if now I draw something which is very wrong, but let me draw it. So now this is my kk minus 1 AG. And I know that inside this set, I cannot put any point. But what it means that I must use this, because my maximal set must have something in this kk minus 1 shifted, so it must be this. So on the one hand, this point is admitted. On the other hand, for maximality, this point is necessary. So for any A, AG belongs to my set, and that means that. That is. So what do I know? That AG is contained in A. And you may ask, why does it mean that they are equal? Because they are both maxima. So if there was a strict inclusion, then AG would not be maximal. So it's enough to show one inclusion. Okay. Theorem 7. That's for non-abelian groups. The two situations where we are happy. One is a finite subgroup. That's completely trivial, because if K is a finite subgroup, then what? Then kk minus 1 is the same as K. The sets K times the elements of the maximal separated set are disjoint. On the other hand, kk minus 1 times the element of the maximal separated set cover. So we have a partition. And this is partitioned into cosets of K. And in each such coset, you just need one point. So if you shift by an element of K, you cannot have identity, because if you have a dot and you shift by an element of K, you must not have a dot, because they are not separated. If you go outside K, you are outside kk minus 1, so you are allowed to have a dot. And you are also allowed to not have a dot. So at any distance G, you have freedom. Okay, and the last case is when G is torsion free. When G is torsion free, actually the argument is absolutely simple, because you take any G, you take a point of you put here a symbol, maybe 0, and of course you can look at, this is my A, G of A, so it's AG, G squared A, G cubed A, and so on. They are all different. So eventually you will go outside kk minus 1A. K minus 1K. Eventually you will go outside. Once you're outside, you are allowed to put here any symbol you want by the specification. So once you're outside, maybe here, you put a different symbol. So if this was 0, you put a 1. But then maybe here, maybe this happens here. But then, of course, somewhere between these points there must be a difference. They cannot be all the same. So maybe here is still 0, maybe still 0, but then here it's 0 and 1. So your point is not invariant under the shift by G. So you can easily find one point which is not invariant under G, and we know that's enough. very rigid. Okay, so we are done with all the trivial observations, more or less trivial. And now is the main theory. So I have to take a deep breath and see if I am able to explain the idea of the proof by waving hands. Okay, so this is much more complicated. It uses the theory of quasi-tilings, and when we have to create something from nothing, so we take our system is x nu g. It's free and ergodic. And we know that the entropy is less than the entropy of our, maybe y, sorry, this should be y. And x is the system with specification inside which we want to find a measure isomorphic to mu. Okay. So what we want is, we want to be able to injectively encode the elements of y by some code, some almost everywhere defined transformation inside our system with specification. Okay, so the first thing we know is that a free ergodic action has a factor in form of a very special quasi-time. So I will call it T. There is a measure, so maybe this is little phi. So this measure is just the image of phi, and the action of the quasi-timing is Benjy. What is, this is an epsilon quasi-timing. What is a quasi-timing? So I will draw pictures on the plane. As we know, it's very confusing, but we have nothing better. Epsilon quasi-timing is a collection, and it is a dynamical quasi-timing. But I will first tell you what is a static quasi-timing. It's a collection of sets which are actually copies of some elements of an a priori selected Fellner sequence. You start with a Fellner sequence. Do I have to explain what a Fellner sequence is? So you choose sufficiently large elements of this Fellner sequence, and you use them as shapes of your quasi-tiling. This quasi-tiling in reality, what is reality? is very difficult to draw, because the proportions between the Fellner sets that you've selected as your shapes is very, very bad. So you have very tiny ones, and the next one is much bigger, and the next one is very big. But I will draw my shapes as relatively the same size. So you cover your group. Sorry? Fractal.
You have small shapes,
Yes, you
big
have
shape.
like this, and the next one is bigger. No,
Draw better small shapes.
yes, they can be, of course, very complicated. Anyway, so what is the rule? The rule is that each of these guys is a large Fellner set. They are epsilon disjoint, which means that if you look at the part covered exclusively by this element of this tiling, then this set is 1 minus epsilon of your original set. And there is also some uncovered part of the space. It has to have small density, actually small Banach density, epsilon. So this is your quasi-tiling, your static quasi-tiling. And then the dynamical quasi-tiling is a collection of such tilings, which is jointly invariant and closed under shifting. So you can imagine that you shift it. You always shift by multiplying the elements by G on the right. So this is a dynamical quasi-tiling, and there is a theorem which says that, oh, there is one essential thing. For each epsilon, there exists a number R sub epsilon. And this choice is completely universal. Namely, if you want the details, R epsilon is the smallest such that 1 minus epsilon to power R is less than epsilon. So for each epsilon, of course, if you take 1 minus epsilon to sufficiently large power, you will get below epsilon. And this R is, say, the smallest for which this holds. So it does not depend on the group, on the Fellner sequence, or nothing. So you can predict a priori how many shapes. So this number is the number of shapes. So this is the cardinality of the set of shapes. This is the set of shapes. And the shapes are selected from the Fellner sequence. These are my shapes. So I know in advance how many shapes I need. That's very important. Okay. So I know that my Y factors to a quasi-tiling with R epsilon shapes, epsilon quasi-tiling, that's for granted. Okay. So this allows me to do the following. Imagine that I have my symbolic element Y. I can think of Y as being symbolic because it has finite entropy. So I can represent it in a symbolic space. Then what happens? I know that with this little y, I have associated a static quasi-tiling, the image of y. So this is phi of y. I use these words static and dynamic to distinguish between something which is a dynamical system, an action of G on quasi-tilings, and static is just one element of that. It doesn't move. So, using this quasi-tiling, I may try to encode that. And here I have my element, my X, my system with specification. So, and the specification has some margin M, which I know in advance. So, what I could do, I can look at my Y inside the type. So I have some symbolic content of this, contents of this set. And I know that the entropy is smaller than the entropy, than the topological entropy here. So that means that if I look at the same shape in X, I will see more patterns than in Y. Exponentially more. So this allows me to take a little smaller set, and this a little is M. I am skipping the details. This is the M interior or M core of the set, something like that. And I know that even the number of patterns in this core is larger than the number of patterns here. Moreover, I can even cut here a small hole. I will explain the hole later. So even the number of patterns that I see in this set with this little hole inside is bigger than the number of all patterns here. So this allows me to choose for each pattern in Y, injectively a pattern on this hollow thing, which is admissible in X. So, okay, now it's a little tricky because I want to do it for each of those patterns. So I have to sort of look at their disjointification and use here for the second one. This is the same group. Okay, I'm drawing on the plane, and the plane is my group, so I can copy this pattern inside my shift. And here I want this pattern to be replaced by an X-admissible pattern in my system with specification. So I have something here which encodes this pattern. I also give it a small hole inside, and so on. So I can create something in X which is sufficiently separated so that eventually I can fill in the gaps staying within X by the specification property. And now if I look at this pattern in X, eventually I fill the whole thing. I should be able, under some additional tricky condition, to reconstruct my Y. Because by seeing this pattern here, I know what was here. Because there was a bijective mapping which used maybe not even all possible patterns in X, but it doesn't matter. Okay, so there are now two technical details which are the most elaborate parts of the proof. The first one is, if I just see the element X which eventually was created, I don't know where the tiling was, because the tiling was just helping me to transfer the information from here to here, but I did not draw the boundaries of these sets. They disappeared. So I need to be able to also encode the quasi-tiling in here. And I can do that by choosing some very special blocks which correspond one-to-one to the R epsilon shapes. I have only R epsilon shapes. So I can predict in advance how many markers I need, and in the center of each shape, so if this is the center of that shape, I put some special set which I call marker, which is admissible in X, and I give it some margin so that later I can fill it in and everything should stay in X. So I need to construct R epsilon very special markers which I will be able to locate by looking at the element of my X. Now imagine how complicated that is, because here I put some information, and how do I know that my marker does not appear accidentally somewhere else? So I must be sure that these are the unique places where I can see some patterns, and this pattern must be resistant to small shifts and to large shifts. So if I shift it a little bit here, my pattern cannot reappear a little bit shifted, because then I will have wrong center, wrong location of the center. So this is resistance to small shifts. It also has to be resistant to large shifts. So if I look here, I am sure that I do not see this much. Moreover, they have to be all different. There is R epsilon of them, because if I look here, I need to know that this is the center of this shape and not of this shape. So there must be R epsilon different patterns which do not overlap with themselves, do not overlap with each other, and they do not appear anywhere else in my X. So this is a little bit technical, but you can do it. It's some kind of, you need some techniques of placing some special things, and the entropy is enough to do it so that you have enough room and so on. And there is one more detail where I cheated, namely the gaps. These gaps between the tiles. By this construction, if I want to reconstruct, because my mapping is supposed to be an isomorphism, so I should be able to reconstruct Y completely, I need to know what was also in the gaps. I didn't encode them yet. So before we start the coding, we have to replace this quasi-tiling by a genuine tiling. A genuine tiling is a partition. And what we want is to replace each tile by something which we call an epsilon modification. So we want to add a little bit to this tile from the gap. So we want to distribute the gap among the neighboring tiles somehow. And we want to partition the overlaps also so that don't overlap. And I want the new shape to be, the symmetric difference to be less than epsilon, divided by the original cardinal. Yeah. So how to do that? Well,
Sorry, so when you do that, do you want still to keep finite number of possible shapes?
no, no. This is why this procedure has to be reconstructable in here when I only know the centers and the R epsilon names of the shapes. So that means that if I see another place with the same configuration, I will partition the gaps in the same manner. So we have with Guohua, we have a construction of genuine tilings, but they have unpredictable number of shapes. And then this won't work because we have only small amount of space to encode the shapes. So we cannot have uncontrollable number of shapes. And here, the construction that I will propose to partition the gaps also produces an unpredictable number of shapes. However, because they depend in a deterministic way, by knowing the original shapes and where they are, you will know how the rest was partitioned. So the procedure has to be deterministic. The disadvantage of this procedure is that your shapes are no longer going to be bounded. So you will have infinitely many shapes. But it doesn't matter. Okay, so here is the construction. I will assume that these shapes are disjoint because I don't want to talk about the overlaps. So suppose that I have some shapes which are disjoint and I have some gaps between them. Okay. So what do you do? The first, first of all, you want to include to this shape from the gaps, not too much. So you want that whatever you include to this shape, maybe this much, is just epsilon in cardinality in proportion epsilon to the whole thing. Because then you can still use the fact that the number of blocks on these enlarged shapes is less than the number of possible configurations in X. Why? Because the number of the enlarged, a number of configurations of this enlarged part is equal to the number of the configurations of the original, plus something that you control. It's epsilon times lambda to the power epsilon something. So you control that. It's not going to be, and you always have this gap. This gap decides about your epsilon. Okay. So you don't want too much to be included to each shape. So how do you control that? So here is the trick that we used with Guohua long time ago. In each shape, you reserve an epsilon elements, epsilon times the cardinality, to be your counter, or to be your, what's that? Abacus. Okay. And then what you do? Well, you enumerate your group, G1, G2, and you take G1. to each element of the gaps between the types, you apply G1. And if you're lucky, you will land in one of those abacuses. If this happens, you include this guy to this type. If it hits here or maybe another empty space, you wait with this element. So in the first step, you will include some number of elements from the graph to your types. But you also sort of cross out this element. It's already been used. Okay, so now you take your G2, and to all elements, you apply the shift by G2, and if you're lucky, it lands in one of those reserved areas, but it must not be an element that has been already used. And if this happens, you include this element to this type. And you continue like that until you exhaust your group. And I claim that in this manner, you will include to each element only as many elements as you have reserved at the beginning. That's clear. But second, each element will eventually be included somewhere. Because, why? Well, first of all, these elements that you have reserved, they have bigger Banach density than the gaps. You can do it. Your gaps are very small, epsilon. You may assume that it's epsilon over 2. You reserve here epsilon of each of those sets. So, in the end, you will never exhaust everything from those reserved sections. Even if you continue, because at most you will use what you have got. And so if there is any point that is left after you proceeded with all your G's, there is a contradiction because there is somewhere an available spot for it. So in this step, which corresponds to this shift, you would have included this one. So eventually you will include everything. And this is how you create a tiling which is deterministically, of course you memorize this order because you will need it for decoding, but it's a deterministic partition of your group into enlarged tiles. Sometimes it may be that this tile gets an element from 100 kilometers away, you don't control it, but still it's a small percentage that you have enlarged. So if you count how many configurations you have on this enlarged tile, it won't be much more than on the original. Okay, so that's roughly speaking the idea. It hasn't been completely typed yet, so there is room for errors still. But we have worked with this already before, so we are pretty confident that this technique eventually works fine. And all the techniques that we are used here have been already tested in other in previous works. So that's it. I don't know how much time I'm missing. Yeah, I told you it will be a little short. So thank you very much.
So are there any questions? Maybe you can say something about, I think it's an open question, like in the context of going from quasi-tiles, and then that you still want the number of shapes to be
Control.
Right? That's a big question.
Yeah, that's a question. So, in general, you see here we have not exactly a tiling because there is infinitely many shapes. Tiling by definition has finitely many shapes. So this is a compromise, but it's because we want something almost surely. So if you want a topological factor, then because this tiling is going to be a measurable factor of this. or this. You still have an algorithm to create something, but it's measurable or finite, because you have this infinite horizon which you need for code. The question whether you can have a finite horizon algorithm to create a tiling from a quasi-tiling is open, and it depends on the answer to the question: are all amenable groups, do they all enjoy so-called comparison property? And that's an open problem for many years. I remember Sasha Danilenko wrote us once an email that he knows how to prove it. And then he withdrew from this claim. So it's really a tricky part, and it's a long-standing open problem. And we can prove that the possibility of continuous encoding or topological factoring quasi-tiling to a tiling is equivalent to the comparison property. So it's not only that it depends on the comparison property, but it actually is equivalent. That's why we cannot answer unless someone answered that question.
So what kind of groups have this comparison property? Because I assume that
comparison, no, or
yes. Yeah, so I assume that the comparison property is some property that is checkable, at least for some groups, is it?
Yes.
So what kind of groups can you give us some examples?
We have a proof that all sub-exponential groups have comparison property.
What is a sub-exponential group?
That if you take a finitely generated subgroup, then the cardinality of, when you take a set of generators, then the cardinality of s to power n grows slower than exponential. So we know for these groups, I think residually finite groups also have, or is it an open problem? It's been a while since we worked on that. All nilpotent groups, for example. No.
Residually finite amenable groups are monotilable, so
Right.
you need only one shape and you tile the group.
Right, exactly, yes. Right. Okay.
So it seems we have no more questions, so thank you once again.
Thank you very much. And I apologize for the chaotic sketch of the course, but if I wanted to make slides with the sketches, it would take me really weeks.